So friends, having had a glimpse into the mathematical basis of oscillatory motion and its special case, the simple harmonic motion, it is now time for us to have a look at a real physical example of such motion. Where do simple harmonic motions occur in nature? As I have said before, it is almost present everywhere. To start with, sufficiently small disturbances to a physical system that is in a state of stable equilibrium produces an approximately simple harmonic motion around the potential minimum. Lot of physics jargon. Stable equilibrium in a physical system generally occurs when the body is in a state of potential minimum, that is, of all possible positions, the position that corresponds to minimum potential energy is the position for stable equilibrium. Normally physical systems occupy that position. What are examples of such physical systems where disturbances produce simple harmonic motion around the potential minimum? Well, one of the most well-known example is that of a pendulum clock. When you shift the pendulum clock slightly around its rest position, it swings back and forth, produces a simple harmonic motion. A marble in a bowl, if you disturb the marble, it goes back and forth till certain frictional forces cancel this motion by dissipating energy. Where else do you find? Well, in one place where you find it plenty is vibrations in an elastic medium under Hooke's restoring force. You see, an elastic medium such as an iron rod or a string or many such materials, when you extend it by a force and a small amount of extension you cause and you remove the force, then the body tends to come back to its original state. It's because under extension or elongation, a force arises, a force manifests itself, which tries to restore the extended object to its original shape. This is of course something to do with atomic structure, but this restoring force is called a Hooke's restoring force. So one of the very common example of studying simple harmonic motion is a block and spring system, where you connect a block to a spring and you extend the block by a slight amount. When the extension is small compared to the length of the spring, then the motion will be simple harmonic, because Hooke's restoring force will come into play the moment you remove the external force that caused this extension. Now, who is this Hooke's? I can't resist the temptation to tell you about this mysterious Hooke's. Hooke's was a contemporary of Newton who did most of his work in the second half of 17th century. He is best remembered for having given the original idea about gravitation, that gravitation of large masses such as planets actually depend on distance. Though he did not formulate the laws of gravitation and it was left for Newton to do it, he is supposed to have laid down the fundamental basis of the Newton's laws of gravitation. Some historians of science, they tell that Hooke's has not got his rightful due among the great scientists of 17th century. Hooke's was a polymath. He was an architect, he was a philosopher, and he was also a biologist. He assembled some sort of a lens to obtain very higher magnification, and he observed beetles and fleas under it, and he depicted very, very minute drawings of these insects and fleas in a book called Micrographia. He published the book Micrographia around 20 years before Newton published his monumental work Principia Mathematica. And this book became a bestseller in Europe. In fact, some people say that the first scientific bestseller was the book of Hooke's, Micrographia, in Europe, something around 1666 or 1667. So let us play a video which pays a tribute to this 17th century scientific genius called Robert Hooke's. Let's see.